Hello everyone. Today we are going to study about the construction of PN junction diode. In the past lecture we have seen how the PN junction diode is formed and what are the symbol of PN junction diode and how the depletion layer is formed. So this figure shows the symbol of PN junction diode. Here it is having two sides, that is P side and N side, which is also called as P region and N region, and the current is allowed to flow from anode to cathode. So today we are going to study how this diode is formed in the industry and what are all the processes which comes under the formation of diode. So this picture shows the different region of diode and the symbol of diode and the actual figure of the diode, which is showing the two electrodes, the two region and one junction. So the construction of PN junction diode involves the following steps: semiconductor material selection, doping, wafer preparation, which is also called as crystal ingot formation, wafer slicing, formation of PN junction, oxidation, photolithography, etching, diffusion or ion implantation. Next is metallization, and last step is dicing and packaging. So let us study about the first step. The very first step is the semiconductor material selection. As we all know, semiconductors are materials which have a conductivity between conductors, generally metals, and non-conductors or insulators such as ceramics. Gallium arsenide, germanium and silicon are some of the most commonly used semiconductors. So semiconductors comes between the conductor and insulator. In this, the mostly used most widely used materials are the silicon and germanium. Silicon is used in electronic circuit fabrication and gallium arsenide is used in solar cells, laser diodes, etc. As we have discussed earlier about the applications of diode, in which for the rectification purposes and as a Zener diode, the silicon materials are used to form diode, whereas for the purpose of light applications or solar cells, gallium arsenide materials are used. So in this way we can say that depending upon the application, the different materials are used for the formation of semiconductor device. Now what all things should be considered for selecting semiconductor? So the considerations for choosing semiconductor materials for development boards are: first is electrical properties. The electrical properties such as doping limits, thermal conductivity and band gap energy all impact the voltage and current levels at which the device and board will operate. So the first consideration should be of the electrical properties. Second is the thermal properties of the semiconductor material. Here the semiconductor temperature and resistivity are inversely proportional. Therefore, a semiconductor material can produce high heat that impacts PCB layout and thermal dissipation and distribution. Therefore, the thermal property is a very important property on the basis of which the semiconductor material is selected. Next consideration is about the moisture sensitivity. Some components are more sensitive to moisture than others, which can affect manufacturing. As we all know, moisture is a parameter which can affect the functioning of any semiconductor device or any electronic circuits. So the semiconductor material which is to be selected, so its sensitivity towards the moisture is should be known. For example, post assembly baking or coating may be required. This parameter can also influence packaging, storage and other moisture protection methods. So moisture sensitivity is another factor on which the material selection depends. Next step is doping. Doping is the process of adding impurities to intrinsic semiconductors to alter their properties. So, as we all know, the classification of semiconductor materials, there are two types of semiconductor materials, that is intrinsic and extrinsic. So, intrinsic are the pure materials in which no impurities are present, and by adding impurities, which is also called as the doping process, the intrinsic semiconductors are converted into extrinsic semiconductors. So, pure silicon or germanium are rarely used as semiconductors. Normally, trivalent or pentavalent elements are used to dope silicon and germanium. So, the elements, that is the trivalent and pentavalent elements, are called as the impurities, which are added to the pure semiconductor materials, that is silicon and germanium. After doping, an intrinsic material becomes an extrinsic material, and only after doping these materials become usable. So, instead of using pure material, the pure material is doped with the impurities, which are the trivalent or the pentavalent elements. In this way, the intrinsic material is converted into extrinsic material, and the extrinsic materials are the materials which are used for the formation of semiconductor devices. Now, the first type of material is p-type material. When an intrinsic semiconductor is doped with trivalent impurity, it becomes a p-type semiconductor. Here, P stands for positive, which means the semiconductor is rich in holes or positive charged ions. As we all know, the p-type material is doped with trivalent, that means one hole will be free and it shows the presence of positive charge. That is why its name is said as p-type material, which is rich in holes or positive charged ions. So, when indium or gallium is added to pure silicon, a p-type material is formed. Here, indium or gallium are the trivalent elements which are added to the pure silicon or pure germanium. So, this type of dopant material has 3 valence electrons. They are eagerly looking for a 4th electron. In p-type material, each hole can be filled with an electron. To fill this whole area, very less energy is required by electrons from the neighboring covalent bonded groups. Silicon is typically doped with doping material in the range of 1 to 106. This means that p material will have much more holes than the electron hole pairs of pure silicon. The below figure shows the doping of p-type material, or we can say that the pure silicon material with the trivalent element, which is indium or gallium. So, after doping, we can see the holes are the free carriers which are left out, and they are eager to recombine with any free electrons. So, we can say that after doping with a trivalent element, the material formed is called as p-type material, since it is having free holes which represents the positive sign, and they are eager to recombine with the free electrons. Next type of material which are formed after doping is n-type material. When we dope intrinsic material with pentavalent impurities, we get n-type semiconductor. Now, here N stands for negative, which means n-type semiconductors which are having negative charged ions, or in other words have excess electrons in it. So, for the example of pentavalent impurities is arsenic. When arsenic is added to pure silicon, the crystal becomes an n-type material. Now, here the word pentavalent means they are having the 5 elements. So, when the bonds get formed, one electrons gets vacant, or we can say that it is a free electron which is eager to recombine with a free hole, and when more than one free electron is present, there is a negative charges, a lot of negative charges arises, and from that the name arises n-type material. Arsenic atom has additional electrons or negative charges that do not take part in the process of covalent bonding. So, the negative charges or the electrons which do not take part in the covalent bonding, they are free to move and they are eager to recombine with any free holes or positive ions. So, in this way n-type material is formed. These impurities give up or donate one electron to the crystal and they are referred to as donor impurities. An n-type material has extra or free electrons than an intrinsic material. An n-type material is not negatively charged. Actually, all of its atoms are all electrically neutral. These extra electrons do not take part in the covalent bonding process. They are free to move about the crystal structure. An n-type extrinsic silicon crystal will go into conduction with only 0.005 electron volt of energy applied. So, only 0.7 electron volt is required to move electrons of intrinsic crystal from valence band into the conduction band. The below figure shows the formation of n-type material where pentavalent elements are added to the pure intrinsic material and n-type material is formed since free electrons are present. This free electrons also represents the negative charges. So, that is why it is the material formed is called as n-type material. The third process is the wafer preparation, which is also called as crystal ingot formation. So, the p-type and n-type doped silicon wafers are formed separately as ingots. This is done through the process like the Sokolsky method or the floating zone method, where pure silicon is melted and a single crystal ingot is grown from it. So, this is a very important process from which the semiconductor or the material for diode is made. So, in this method the silicon is melted in a we can say that a vessel, and a seed is dipped into it and it is slightly removed from it and a one ingot is formed. So, the picture below shows the steps by which the crystal ingot is formed. High purity silicon is melted down in a crucible. After that, a seed crystal mounted on a rod is dipped into the molten silicon. After some time, the rod is pulled upwards and rotated at the same time. It is just not only pulled upwards, but in the rotational form. So, what happened after this? A large single crystal cylindrical ingot is extracted from the melted silicon by precisely controlling the temperature, and also the rate of pulling and speed of rotation is also controlled. So, these are the factor on which the ingot formation depends, that is controlling the temperature, the rate of pulling and also the speed of rotation. The fourth step is wafer slicing. As the crystal ingot is formed, now the grown crystal ingots are sliced into thin wafers using a diamond saw. Now, the semiconductor materials, as we all know, practically when we see a diode, it is a very small device. It is very small in shape, but it is formed from a large ingot, or we can say that a crystal. So, the grown crystal ingots are of a large size. From that, the thin wafers are sliced, and this process is called as wafer slicing. So, what happened here is that a diamond saw is used, mostly the diamond saw is used to slice the grown crystal ingot into thin wafers. Now, these wafers act as the base material for individual diodes. So, from this thin wafers, they act as the base material, and from this the diodes are formed. Now, the next step is the formation of p-n junction. The p-type and n-type wafers are brought together and physically joined, forming a p-n junction. This process is often referred to as wafer bonding. So, what happened here is that after wafer slicing, thin wafers are formed. So, thin wafers of p-type material are formed separately and thin wafers of n-type material are formed separately. So, in this process, that is the formation of p-n junction, which is called as wafer bonding. This p-type wafer and the n-type wafers are brought together and physically joined, and this process is called as wafer bonding. The junction is typically formed by bringing the two wafers into close proximity under controlled conditions, allowing the diffusion of dopant atoms across the interface. So, during the wafer bonding process, when these two layers are physically joined and they are allowed to come into close proximity under controlled conditions, the diffusion process takes place, and the diffusion process is allowed to take place where the excess electrons move from n region to p region and the excess holes move from p region to n region, and after that a junction is formed. So, the below figure shows the process of wafer bonding. This diffusion process creates a region near the junction that is depleted of majority carriers, forming the depletion layer. So, here two wafers are taken, that is wafer 1 and wafer 2. They are physically joined, or we can say that they are brought closer and physically joined, and before bonding, as we can see, there is a gap between the wafer 1 and wafer 2, and once the bonding gets started, the gap got removed and they form a single element. We can say that one layer is of the p type and another layer is of the n type, and between that a junction is formed, which is also called as and that layer is called as depletion layer, and the formation of depletion layer completes when there is no majority carriers to move from n to p and from p to n. Now, the next process is oxidation. A thin layer of silicon dioxide, that is SiO2, is grown or deposited on the surface of both wafers. So, if we have selected the material silicon, so in the oxidation process silicon dioxide is deposited on the surface of both wafers. This layer acts as a protective barrier during subsequent process. So, to give a protective layer or protective barrier, the layer or oxidized dioxide layer acts as a protective barrier during subsequent processes. Now, the next process is photolithography. Photolithography is used to define the diode's dimensions and shape on the wafer. As we know, the diode is very small in shape or size, so and it has a particular dimension. So, during the process of photolithography, the dimensions of diode is defined and it is molded into a particular shape. A light sensitive photoresist material is applied to the wafer surface and a mask with the desired diode pattern is placed over it. After that, ultraviolet light is then used to expose the photoresist through the mask, creating a pattern on the wafer, and from that we can identify the p layer and n layer, and after that the photolithography method, the diode dimensions are defined and its shape is defined, and we can clearly see the layers on it. Next process is called as etching. The exposed photoresist is developed, leaving a patterned layer on the wafer. So, after photolithography, a patterned layer is formed on the wafer. The etching is then performed to remove the silicon dioxide layer and expose the regions of the wafer where the p-n junction will be formed. After the photolithography process gets completed, the silicon dioxide layer is removed and it exposes the regions of the wafer where p-n junction will be formed and it is physically visible. Next process is diffusion or ion implantation. So, for diffusion or ion implantation, these are the two methods. There are two common methods to introduce dopant atoms at the exposed regions. First is diffusion. In this method, the wafer is placed in a high temperature furnace with a specific gas containing the desired dopant element, that is boron or phosphorus. The dopant atoms diffuse into the exposed silicon regions, creating the p type and n type layers of the diode. In ion implantation method, dopant ions, that is boron or phosphorus, are accelerated and bombarded onto the exposed silicon surface. The ions penetrate into the silicon lattice, creating the p type and n type regions. Now, the next process is metallization. The metal contacts, usually aluminum or gold, are deposited on the front and back sides of the wafer to provide electrical connections to the p type and n type regions. As we know, once the wafer formation process gets over and actual layers are seen, now to connect this diode with the circuit, with any circuit, connections need to be done. For that, the metal contacts are formed at the two ends, or we can say that front and back sides of the wafer, and this to form this metal contacts, aluminum or gold is used. This metal contacts act as the anode and cathode of the diode. As we know, the two electrodes in the diode are anode and cathode. So, this metal contacts acts as anode and cathode, and the current flows from anode to cathode. The last method is dicing and packaging. The wafer is diced into individual diodes using a diamond saw. Now, here once the diode is formed in the form of wafer, it is diced into individual diodes using a diamond saw. Here each diode is then mounted on a package and encapsulated to protect it from environmental factors and physical damage. So, once the diode is formed, it is packed, and so that it can be protected from the environmental factors and physical damage. As we know, the diode is to be transported or used until and unless it is connected to the circuit, it should be handled very protectively, or we have to protect it from external damage. So, it is packaged in that manner, so that any environmental factors should not affect the working of diode. So, after completing these steps, the p-n junction diode is ready for use in various electronic circuits and devices. As we have seen the actual picture of the diode, there are two electrodes, that is anode and cathode. So, from that directly it is soldered or connected into the electronic circuits, and the diode is ready for use. So, in this manner the diodes are formed, and or we can say that it is constructed from a base material to the final product as a diode. When the diode is connected in a circuit or any circuit for any application, and after that when a voltage is applied across the diode in the forward bias direction, it allows current to flow freely through it. Now, here the word arises forward bias. The forward bias connection is the direction in which the current is allowed to flow from anode to cathode, and in the similar way another direction is called as reverse bias direction. In this direction, when the voltage is applied in the reverse direction, that is in the reverse bias direction, the diode blocks the current flow except for a tiny reverse leakage current. So, the diode can be worked on can be allowed to work on both the direction. In one direction, it allows the current to flow from one direction to another direction, and in the another direction, which is called as reverse bias direction, it blocks the current to flow accept a very small current which is flowing, which is called as the reverse leakage current. So, in this manner a diode is constructed from a material, semiconductor material, and it is converted into end product which can be directly soldered or it can be connected to the circuit, and it is ready for the operation or for any of the applications, different applications for which the diode is made. Now, as we have seen, when as the diode gets constructed and as we have discussed about the forward biased and the reverse biased condition. From this we can simply understand one more thing is or the one application for which the diode is selected is as the switch. As we know, switch it has two operation, on and off. So, let us take the on option as when the current is allowed to flow in the circuit. So, when the diode is forward biased, is connected in the forward biased direction, it allows the current to flow freely from anode to cathode. But when it is connected in reverse bias direction, now what is reverse bias direction? When the positive sign is made connected to the N side and negative to the P side. So, in the reverse bias direction, simply the reverse means when the diode blocks the flow of current. So, in this situation the current is blocked by the diode, and practically if we see a small amount of current which is called as reverse leakage current is flown, and it acts as a open switch. Open switch means no current is flowing from the diode. So, this is one of the application we can understand from here, that how the diode acts as a switch when it is worked under the forward bias direction and when it is worked under the reverse bias direction. Thank you.